seminar. Oh, very good. Yes. Good. Okay. Good morning, everyone. Thank you for attending the seminar. Today, I'm honored to introduce Professor Juan Munoz from the Católica University of Santiago in Chile. Thanking him for the long trip to make it to the United States. Professor Muñoz received his PhD in civil engineering from UC Berkeley in 2002, and since then he has been a faculty member in the university in Chile, and he has a lot of achievements. So very quickly, he has been, for many years, he has been the advisor of the government of Chile on public transport issues. So his interests are public transport, network modeling, and traffic flow theory. Without further ado, let's hear his presentation.
Thank you very much, Luis, and thank you very much for coming to the talk. It's a pleasure and an honor to be here at the University of Minnesota. The work I will be presenting is a work that has been done within these two centers here, the BRT Center of Excellence, which is Fast Rapid Transit. It's a center funded by the Volvo Research Educational Foundation, a Swedish organization, and also the Center for Sustainable Urban Development in Chile. The talk, as I said, I had 50 minutes, which was a lot of time. So if you have questions or concerns, maybe we can interrupt me and see how long I can get. I mean, I have more material than what I think I can achieve. So eventually, if the time is not enough, I will be skipping some of these parts. The idea is to bring you a general understanding of the impact of what I call headway variability. The headway is the time between two vehicles of public transport passing out to the same place, and how it affects waiting, crowdedness, and reliability. The impacts are very severe, and at the end I'm going to present two strategies that we've been working on in these centers to control this phenomenon. So this is work I've done with some of my colleagues, Felipe Delgado, Ricardo Gibson, Sebastián Pavó, and two students, Jaime Sosa and Diego Morales. So the main issue here, and that's part of one of my main interests, is that I'm convinced that cities need great public transport. They really need great public transport, and the cities need their citizens to use public transport. Now, this is not going to happen spontaneously, right? Unless people think very highly about public transport, if they are satisfied with the level of service they receive. And now, this forces us to think of what do people seek when they're using public transport. And this is a slide I made, and I've used many times. I made this when I was at MIT working with Professor Wilson here for a sabbatical, and I started saying, well, we need public transport to be fast. People need a fast trip. People want low waiting times. People want a comfortable trip. People want reliability in the experience. I think these are four attributes, or maybe the four key attributes people are waiting that are directly related to the operation. Because there are many others, like safety. But if we think of operations, these are the four attributes that people will be looking for. And if you want a fast trip, then how do we achieve these attributes? If you want a fast trip, then you need to decrease travel time. For low waiting time, you increase the frequency. Because if you increase the frequency, well, the buses will become more often, and people will be waiting less. For a comfortable trip, what you need is to increase transport capacity. And for a reliable trip, you need to decrease travel time variability. Now, how do we get this? To decrease travel time, well, you need to increase the speed. Speed is key for having a fast trip. If the speed is low, no way you're going to get a low travel time. How do you get a higher frequency? And here there's two ways of getting a higher frequency. One is increasing the fleet, more buses, more vehicles, more trains. Another one is to increase the speed. If you increase the speed, your vehicles will be doing more turns per hour, and you will be increasing the speed without any extra fleet. How do you increase transport capacity? And here you have three ways of increasing transport capacity. One is to increase the fleet, increase the vehicle size, or increase the speed. You increase the speed, you have more frequency, more transport capacity, more comfort. And that's why worldwide we've been searching public transport for speed. And that's why we call about bus rapid transit. So rapidness is at the core of BRTs. That's the core of what public transport should be achieving. Not just because we want a fast trip, but because by achieving speed, we get not only a fast trip, but also low weights and comfortable. And that leaves us with the last column there, where for reliability, what we need is to have regular headways. And the focus has been so far increased speed, and well, if we have some spare time, maybe focus on regular headways. And today I'm going to argue that this is the wrong way to approach this, and this is as key as speed, and we need to reset the focus. So that's why we've had bus rapid transit. These are pictures from around the world, most of them in South America, but not all of them, where what you do is to provide buses with a segregated way from cars, where they can have this fast speed, where you can have a very high capacity. This service over here, called Transmilenio in Bogotá, moves 45,000 passengers per hour in each direction. This is huge. This is really, this is metro level. We have in Santiago a metro which runs at 6 passengers per square meter, with 8 cars per train, 1 train every 2 minutes, 45,000 passengers per hour. This is amazing achievement for a bus operation. Of course, not very comfortable at all. Very crowded. Huh? But it's amazing that cities have moved towards BRT because of this very cheap or more inexpensive way of achieving high level of service in the surface. Another important thing that I would like you to think of is that when you put your high capacity public transport underground, which is what many people argue for, you leave the streets for the cars. And if you want to have more sustainable cities, you need people to leave their cars at home. So BRT has also one extra thing, which is it competes with the car for the surface of the city. So the question here is BRT enough? And the question is, what about reliability? What are the impacts of an unreliable service? Is what I'm going to be talking on the first half of my talk. And I will show its impact can be devastating for the level of service. Devastating, and I'm not exaggerating with the word. So to achieve these attributes, my argument will be you need to increase speed, you need to provide regular headways as well. Now the question here is, why are headways so irregular? And this is something that happens everywhere in the world. I'm not sure, I haven't experienced Minneapolis that much, but I would guess it happens here too. That instead of having buses coming regularly every certain number of minutes, they come very often couple or even sometimes 3 together. And the reason for this is that when you operate public transport, and this is something that is not intuitive to realize, vehicles behave like magnets. You dispatch them like this, 5 minutes, 5 minutes, 5 minutes, and they look like positive, negative, positive, negative, positive, negative. Very, very soon they will go like this. And the reason for this is very simple. When you dispatch them every 5 minutes like this, this happens especially when you have no schedule. Because if you have schedule, you have add some slack in your itinerary to prevent this, hopefully, right? But in the case of non-schedule, because of its high frequency, and you usually do not provide schedule for frequencies higher than, let's say, 6 buses per hour, then what happens is that if this is 5 minutes, and this bus over here gets a red light, that this one doesn't, all of a sudden, this headway, instead of being 5 minutes, is now 3 minutes, and this one is 7 minutes, and instead of 5. When that happens, this bus, which arrives to a next stop, this headway, because it's 7 minutes, there will be much more people waiting for the bus. So this bus will take longer to load the buses and for passengers to alight. This one, quite the contrary. It arrives to the next stop, and it's only 3 minutes, so there are very few people waiting for the bus. And therefore, it will speed up very easily. So this is what we call in engineering an unstable equilibrium. It's an unstable equilibrium. You develop any kind of perturbation, and the system will never come back to its original position. So any perturbation and the equilibrium is lost, and this happens all around the world. We have 255 buses in London. Here we have several in Beijing. Here we have my favorite pictures of Boston, Massachusetts, just in front of the Temple of Engineering at MIT. This is in my city in Santiago. Everywhere I would bet that if we have high-frequency service in Minneapolis, we will have this too. So at this seminar, I will address why does bus bunching happen, what are the impacts, and does it have a solution? And of course, here I'm going to divide this into two different approaches we have developed in my research group. So why does bus bunching happen? One of the first reasons, especially in the developing world, is that these are very informal companies that are operating, and usually they put the newest guy, the one nobody respects, to dispatch the buses at the terminal. And very often they come out from the terminal dispatched together. Like, so if you were supposed to provide one bus every 5 minutes, well, they were dispatched 2 together every 10. And 2 together every 10 is really, really bad for the passenger, because instead of waiting a maximum of 5 minutes, well, now you're waiting a maximum of 10. The first bus will be packed, the second one will be half empty. And your reliability has vanished. So very often, and in public transport, I like to mimic this with Forrest Gump. Forrest Gump, remember what he said? Life is like a box of chocolate, you never know what you're going to get. Well, public transport shouldn't be like this. But it often is. You never know what you're going to get when you go to a bus stop, how long you will be waiting, what kind of experience would you have in terms of crowdedness inside the bus. Second, and this is very important, speed variability. So what I will argue is that along the route, the reliability gets worse, and this is because of speed variability based on the travel time variability and dwell time. In terms of travel time variability, for many reasons, because of congestion, not all the buses face exactly the same travel time between 2 consecutive stops. As I said before, traffic lights, sometimes you get the red, sometimes you get the green, and also driver heterogeneity. Some drivers are more aggressive than others. At the end, what you have is that the travel time between 2 consecutive stops is far from being similar. And when the vehicle arrives to the stop, well, you will get some time for boarding and alighting, and of course, since passenger arrival is very stochastic, you never know how many people will be there. If there's a metro station here, and this is going to be filling the bus, of course, if the metro just arrived, this is going to be full. If another bus took these passengers and now the stop is empty, well, it's going to be very fast. So we have this variability that will be creating what we call bus bunching. By the way, this bunching also happens with metros. In our city, metros operate every 2 minutes. And very often what you have is that the interval grows. It never diminishes to get 2 trains together because of safety reasons. The control system will never allow this to happen. But what they usually cannot avoid is a certain headway to get much, much, much longer, especially because at metros, when you have a really packed metro, then it takes a long time for people to board and alight because of the friction between passengers. This can take quite a lot. So what are the impacts? And I will argue that the impacts are various, and it affects users, it affects operators, and as I will show you within some minutes. So, and now I need you to concentrate. It's going to be a fun example in which I will assume that we have a bus service that will visit a stop. And in this stop, we will assume that we have a 5-minute average headway. So every 5 minutes, a bus should show up to take the passengers from the stop. We will assume that we have 80 passengers capacity vehicles, buses, and an average demand of 50 passengers per bus will get to each of these buses. This is the first stop of our terminal, of our service. Okay? So if this is the case and the buses come every 5 minutes, well, as I said before, we have 50 passengers going to each bus, and our buses will be half full, more than half full, like 62% full, because there are 80 passengers, only 50, great, and people will be quite satisfied. Now, what happens if instead, the same service, instead of coming every 5 minutes, come every 2, every 8, every 2, every 8, every 2, every 8? If that is the case, what we will see is the same supply. In terms of indicators, for the agency, they'll say, we're still offering 12 buses per hour. We're doing great. Our buses are 62.5% full. We're doing great. However, this bus will have 20 passengers, this bus will have 80. This bus will have 20 passengers, this bus will have 80. And people won't be waiting as much as 5 minutes, but instead as much as 8 minutes. And notice that those people that are angry because they waited more are the same ones that are angry because they're experiencing a crowded bus. So there's correlation here. So now we have a very full bus, an empty bus. A very full bus, an empty bus. Of course, this is not as, it's never as deterministic as this, but this explains you what the problem we're facing. So what do we see is that we plan for this, we get this. We have increased average occupancy. In average, there's still 62.5, but please remember that here we have only 20 people, here we have 80. So even though the operator may say we have 62.5% occupancy, the occupancy experienced by the users is much higher, because 4 out of 5 says 100%. So the average is different if I average across buses or if I average across passengers. So most users suffer high occupancy. It has increased the occupancy variability. As I said, for example, you never know what you're going to get in terms of occupancy, generating a lot of uncertainty. It has increased waiting times. 1 minute of waiting is perceived as 2 or 3 minutes of in-vehicle time. So what I'm saying here is that when you understand how people behave, people tend to wait more, their experience waiting, than in vehicle. So this is very relevant. The moment, if you are a public transport user, you know that when you're waiting for the vehicle is the moment when you feel more vulnerable. When you feel like left alone in the ground waiting for somebody to come. So it's a very difficult moment. It has increased the waiting times, it's increased the variability of waiting time, which will probably lead also to earlier departure for users. But if this is the case, you need to be at a certain time at the destination, you know that you need to prepare for 8 minutes, which is the worst case, not for 5. So it increases dwell times, boarding and alighting is slow and creates friction between passengers when these full vehicles pass through to bus stops, and increase the variability of dwell times as well. So when we talked about the cities needing their public transport systems to be liked or by the users and they being satisfying, this looks like a very relevant problem. Now, how does it affect user satisfaction? And here I'm going to argue that things get worse. So let's assume, and I'm going to put here only occupancy. As I said, we have waiting time, reliability, occupancy. Let's put just occupancy and see how user satisfaction is affected by occupancy. When the vehicles are quite empty, satisfaction is quite high. And probably every extra person you add in the bus has a marginal growing impact in this utility. So when you're the 80 passenger bus is 20 people, an extra passenger or 5 extra passengers from 20 to 25 is irrelevant. From going from 75 to 80, it makes a big difference. So, and let's go to our example where we have, well, we plan and we're the agency and we say, boss, we decided to implement, to plan for buses getting only 50 passengers in average. Therefore, we're very happy because people should be very satisfied because according to our imaginary curve of satisfaction, people will rate us with an 80% satisfaction. Great, well done. However, if it's instead of being 1 bus every 5 minutes, what we have is 1 every 2, 1 every 8, 1 every 2, 1 every 8, this is what we have. Half of our buses are here, half of our buses are there, with 20 passengers and 80 passengers. And let's assume here that these 20 passengers are 90% satisfied, they're very, very happy. These 80 passengers are 10% satisfied. So now, instead of having this 80% satisfaction, if we average the buses, we get 50%. We have dropped 30 points of satisfaction just because of the unreliability. But furthermore, this is if we weight these two as equal. However, we know here we have 80 people, here we have only 20. So things are much worse, as I argued before, and you end up with a really, really lousy public transport service. You wonder why people hate the system. Just because of unreliability. Just because we didn't pay attention to something that seemed like a detail, but it's not. So to achieve these attributes, as I said, we need to increase speed and provide regular headways. And now I'm going to shift to the second half of the talk, in which I'll be talking about two different ways in which we have worked to increase, or to improve this solution. And these are going to be, does it have a solution? Yes, there's many ways. One is, as I said, as with BRT, to improve headway regularity is to provide dedicated infrastructure. We have observed that if buses were to operate in a segregated path roadway instead of in mixed traffic, it's much easier to provide a reliable service. You can also provide transit signal priority, and this is interesting because it allows you to deal with this without any humankind intervention, which is always tricky. Now, the solution I'm going to show, I talked to a person in the MTA in New York, and they said we could never ask our drivers to do what you're asking us to do. However, we can ask our transit signals to do it. So because transit signals don't complain that much, and therefore we can eventually trick our traffic signals to give priority to the delayed buses and to slow down those that are coming, are about to reach the bus ahead. And the third one here is, which is I'm going to be talking, is to develop some sort of real-time control. And you can do this at the dispatching, you can do this along the route, and I'm going to show you a little bit of the tools we've developed in a spin-off from the university we developed called Bus Assist. So the two strategies are going to be holding and boarding limits, and the second one is going to be vehicle injection. Let's start by holding and boarding limits. So the approach here to deal with this, so holding is every time a bus reaches a stop, you ask yourself, should we hold this bus a little, or should we let it go? Of course, if it's a bus that is ahead of the immediate position between the immediately upstream and immediately downstream bus, you may want to hold it. If it's coming back behind schedule, or there's no schedule here, but behind that ideal position, you will never hold it, right? And boarding limits is something that is more difficult to do. I have it only for modeling purposes, which is that in some cases, you may want to prevent passengers to board a vehicle, even though there's capacity, even though there's room, just because you want this very delayed bus to speed up. And this is something that bus drivers sometimes do. When you have two buses arriving together, the bus on top will say, don't board this bus because we're really full. Board the one behind, you'll have a lot of room right there. And that allows not only to have a more comfortable ride, but also the first bus will now be able to speed up a little bit and get to a better position in the middle of the two buses ahead and behind. By vehicle injection is, well, you have 20 buses for this route. Why don't we operate only 19 and leave one of them in an intermediate stop waiting to be injected in the service if a too broad headway shows up. So in the first case, I'm going to talk about bus holding, vehicle holding and vehicle and boarding limits for passengers. We did this through a mathematical programming rolling horizon model. This is something we did with Felipe Delgado and Ricardo Giesen. It's a model that includes capacity constraints. So the idea here is to develop a mathematical model from which we will get the signal of how long should we be holding a bus when it reaches a stop. We will assume that the buses, of course, have a given capacity, and this capacity is strict. And we will do this with no binary variables, and this is very relevant because you really want to have this decision in real time. So you don't want the bus to be there and say, I'm going to call Cplex, it's going to take 25 minutes, wait a minute. That doesn't work. You need to have it very fast. So the issue of being able to provide a model with no binary variables was, I think, was very good. And decision variables here are how long should we hold the bus, and this is an if we want to implement this, we may never do it, but if we want to implement this, if we want eventually to tell the system that some passengers will not be able to board. By the way, this is also something that metro systems sometimes do. If you have traveled around into really crowded metro systems, sometimes passengers are prevented to get into the platform at the mezzanine level to avoid too many people, for instance, in the platforms for the trains. So we have a one-way loop transit corridor. where with buses, a certain given number of buses are operating in the circuit. We have a certain number of stops, a single service, and stops, and k homogeneous buses. We can do this with heterogeneous buses, but let's assume that we have homogeneous buses, okay, in terms of capacity. And we have real-time information about where the buses are. So what we really know is where our buses are. The other thing we know, or we don't know, but we can estimate based on where the buses are, is that we will assume that we have an origin-destination matrix, or from bus stop to bus stop. So we know, in average, during the morning peak, how many people travel from station 1 to station 2, station 1 to station 3, station 1, all the pairs of stops. If you know that, then you can estimate the expected number of passengers in each of the buses, because you know where the buses were in the past. So when a bus arrived to a stop 5 minutes after the previous one, and you know in this stop 2 passengers arrive in average per minute, well, it's reasonable to think that 10 people boarded that bus in this stop. So what we can estimate is, what are the bus loads? It's an estimation. Of course, if you have APC system, passenger counting, that would be even better, because you eventually can have a more precise estimation. We can estimate how many passengers are waiting at each stop. We can also estimate where the passengers will be alighting each of the buses. These are estimations. And we will assume that for the dwell time, every time a bus reaches a stop, we will assume that the boarding time dominates alighting time, so the time the passengers will be, the time the bus will be at the stop, is linearly dependent on the number of passengers that will be boarding. We will assume that buses serves all stops, so you never skip a stop, because sometimes buses don't serve a stop if nobody is asking to stop. Here we'll assume in our model that buses will stop at every stop, which in very busy conditions, that's what's usually the case. We will assume that overtaking is not permitted. Sometimes it's something that happens when 2 buses come together, that the one on the back may think that a good solution is to overtake. Lazy drivers don't do. They relax, go back, empty bus, nobody complaining, and go, in Chile they call it go like mochila. It's a backpack. They go like backpack with the previous one, which is really, but when these 2 drivers arrive to the terminal, they usually get some sort of argument or fight. Because the one ahead realizes that he's doing he's getting all the insults, and people being very angry, because every time arriving at stops, people are saying, finally! And so crowded. While the one in the back is having a very relaxed time. So, but if the guy overtakes, notice that overtaking doesn't really solve the problem. Because then this bus will face the very long headway and will still get delayed. So it's better if they can leapfrog like this, of course, but it doesn't really solve the problem. And we will assume that the capacity of the buses is strict. So the objective function here, so let's go here. The goal is, every time a bus will reach to a stop, we will call our optimization model. And the question would be, should we hold this bus or not? And for how long? And the way we'll do it is that we will solve an optimization problem in which we will be considering the process of all buses until they reach a certain amount of time, or until they reach to the terminal, a certain rolling horizon in which the model will be asked to identify how long should we hold each of the buses when they reach the bus stop, so that the objective function, which in our case would be travel time or waiting time, is minimized. So that's what we want. We want to decide how long should we wait, should we hold the buses, so that the waiting time of all people here is minimized. So the first part is, what's the waiting time experienced by passengers as they wait for the first bus to arrive. And we will make this distinction because sometimes people are waiting for the bus. But if this bus comes full, well, I have to wait for the next one. I'm assuming that the weight of my waiting time is much higher for the second one. I really get upset if I cannot board the first one. So I'm going to say, well, this is the waiting time for the first. Notice that this is quadratic. This is quadratic. Why is it quadratic, the waiting time? Because the difference between the arrival time of a passenger minus the moment the bus arrives tells us how much time a person waited. However, the number of people waiting is also proportional to the same number. The longer the wait, the more people are waiting. So if you're considering the total waiting time across all passengers, this is going to be a quadratic expression. And everything else here I would say is detailed in the same idea. It's a quadratic expression on how many people are waiting for the first bus. We also have here in-vehicle waiting time for passengers aboard the bus being held at stop. Of course, if you are inside the bus, you don't want buses being held all the time, so that's also annoying. Here we will assume that the number of people inside the bus are waiting for a certain number of time, which is holding. Okay, and this is the same idea. People may be prevented from waiting for the first bus. I have to wait for the second bus. This is going to be here, the number of people that are prevented from boarding, how much extra time they will have to wait. And we have added this last element, which we call the penalty for passengers left behind if there's available capacity, which is the number of people that, even though there's room, they're prevented from boarding the bus. If we want this never to happen because we think it's unacceptable, we will going to put here a very big M, waiting for this never to happen. However, if you're open for this to happen, you just leave it as a possibility. So this is a model that works for only holding or full holding and boarding limits. Same model. So these are the four elements. They're waiting for the first, waiting for the number of waiting being held at the vehicle, and they're waiting for the second bus to arrive, and this penalty for boarding limits. And these are the restrictions, which I would like, instead of going through the math, I would like to explain them little by little. What they do, this constraint, is they allow that the evolution of the system will be feasible, will be reasonable. For instance, that there's a certain internal consistency of the variables, like for instance, defining how much time, when will be the departure time of each bus from each stop. How do I compute the bus loads? How many people are inside each of the buses across the evolution, this rolling horizon for all buses? If there's the available capacity, as I said, the penalty for boarding limits was proportional to this. If there's room or if there's no room for passengers. The potential passenger demand, how many people would like to board each of the buses at each of the stops. The number of passengers alighting a bus at the stop. Remember, we assume that we know how many people will be alighting the buses at each of the stops because we assume that we have a given origin-destination matrix. The passengers prevented from boarding, the passengers allowed to board, the dwell times, and buses cannot overtake. We assume that buses, the order will stay identical. And now I'm going to show you the result. This is a simulation that Nigel has observed, has watched for 23 times. This is number 24. I'm very happy, Nigel, for your patience. But I think it's a great animation. This animation, what it shows, these squares over here are stops. The circles over here are buses. The color of the bus is how the bus load. Green, of course, is empty. Red is going to be very heavily loaded. And the buses will start operating this way. At the beginning, in both cases, it's going to be the same animation here and here. And the randomness, the only randomness, comes because of the number of people arriving to the stops. So we will assume here that the travel time between consecutive stops is deterministic. The only the single randomness is arrival to stops. And of course, a random arrival means a random dwell time, and therefore our buses will start to bunch. For the first 15 minutes, both animations will be identical. And from minute 15 and on, in here we will start applying the optimization model I just introduced. Every time a bus arrives to a stop, they will call the optimization model and ask, should I hold the bus, yes or no? The top here will keep on rolling without any control at all. What you will observe is at the beginning, very fast, these two identical simulations will show a lot of bus bunching, but after minute 15, you'll see that this one will start to behave much more as you would like. So let me see. So here goes, number 24, Nigel. So this is minute 2, 3, 4, 5, and you see buses started to punch and started to get very heavily loaded. So this is our buses. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Where's number 15? Right there, behind number 15. And the first thing from now on, I'm starting to control these buses. Every time a bus arrives to a stop, from now on, I will decide to hold it or not. Notice the first thing it will do, it will split this one, because I will hold one of them. Okay? And then we'll see what happens. Look. Did you see it? So from now on, I'm controlling at the bottom, I'm not controlling at the top, and notice how different the level of service that people are, or how reliable this service is in comparison to this one. So this is very common, or very similar to what Alireza sees in Tehran, very common to what I see in Santiago. I'm not sure about Minneapolis and St. Paul, but this is in the developing world. This is what, look at the long headways here. If you risk this level of unreliability, you need to leave your home much earlier to be sure that you will be getting to your destination on time. And notice also that this is an extremely loaded bus that come here behind. So, and I'm going to show you now some of the results in terms of indicators. So this I'm going to show no control with this real-time holding. These are time-space trajectories. Each of these lines is one bus. And this is the first stop, this is the last stop. And when these bus stops are right there, then they are dispatched from here, because it's a circle. So here, we usually, if we have the bus, we'll dispatch it according to a certain headway. So very often, if you don't control, you still hold, and this is very important, you still hold here. Because when you have 3 buses arriving together, well, you won't dispatch the 3 together here. So you will be holding the buses here at the terminal just because 3 of them arrived together. So now what I'm going to argue is that the holding you do here along the route, in this case, you do more than that because of the holding you do at the terminal. But notice how even the system can be, even though there's randomness in comparison to this. These are the bus loads. This is the number of passengers inside each train. How much time do we have?
10 minutes.
Okay, it's going to be a little bit fast. So this is the bus load. First station, last station. You can see that some of the buses never get up to more than 20% of the load, while many others get really, really crowded. Force them. While if you do some control and you take some actions, this will happen much less. And this is very important for the operators. This is the cycle time. The cycle time is a key element for bus operations. First, because the frequency you can offer is the number of buses you have divided by the cycle time. So you double the cycle time, you halve the frequency. So you really want to have a low frequency, a low cycle time. But also, if it has a lot of variability, like this one, then you never know at the terminal when the next bus will arrive. How many drivers do you need to be dispatching a given frequency? So in this system, you need more reserved buses and more reserved drivers than if you have this kind of distribution for the cycle time, which, by the way, it also reduces the mean time of the cycle time and also the standard deviation. So we have developed some tools here in which we have implemented in some services systems in the world, where we provide this information to the driver to slow down, to be okay, or to tell them that they're eventually late. And we have put them here in front of the drivers to improve the level of service in a couple of services in Santiago and in some other parts. Notice this is also attractive. This is real data from Santiago, where we have the distance from the origin, and in Chile, in Santiago, we are requested to bus operators are measured their variability in 3 points along the route of a bus service. Immediately after dispatching, at the moment they arrive to the terminal, and in an intermediate point. And you can see when you look at the excess waiting time, how it grows across the route. So the more passenger, the farther the buses are from the initial terminal, the larger it is the excess waiting time for the passenger. So this is something that is quite problematic, but also very important that they do a very lousy job at the dispatch. Because we have an excess waiting time beyond what is the minimum you would achieve if you get a regular dispatch. So this is something, this goes the distance from the first stop. You can increase the waiting time, and the headway regularity grows at dispatch. So we have developed some tools for allowing operators to dispatch buses on time, which is suggesting when to dispatch buses, and also forcing the operator to give some reasons why this is not working very well. So, and the interesting thing here is that all these tools are built to be operated without a schedule. So you do a schedule of your buses or your drivers for the planning of when the drivers should come to work, but you keep on updating what should be your dispatching time depending on what's actually happened in the city. And this is being used in Santiago, in Lund in Sweden, and some other cities in Santiago. So this is I like to tell this story because we're making an effort on making our research build this bridge with the reality to improve the conditions of public transport. And the last, which I have very little time, so this one I will, how many minutes do we have? I have no minutes.
7-8 minutes.
So this is going to be very fast. This is, well, it shouldn't be fast, but this is the idea here is vehicle injection. A paper that appeared in Transportation.Research.c recently this year. The idea is that one or more buses are kept at specific points along the route waiting to be injected. When a long interval comes, the idea is to react at extreme cases. This is when you don't have any other control mechanism. This is the only thing you can do. By the way, in Santiago, Metro does this. We reserve some trains in specific stations to inject them when a long headway comes. It's quite simple, but it's only used in specific locations, and also you may lose an operating bus. Like you may see that you never used it, and you, instead of having 20 buses operating, you had only 19. So the questions we have here are: what headway should trigger an injection? What is the impact of keeping several buses for injection? Is it better than just operating all the fleet normally? So we have a couple of models here. The single stop model. The idea is that you have a headway distribution that you assume known, which is maybe historic information. You know what's the distribution of the headways. We will assume that we have n buses that will pass during a certain period of analysis. Let's say you're simulating or 2 hours, and you will have 20, 30, 40 buses going through the stop. Here I'm assuming a single stop, by the way. Then later I will assume a more complete scenario for the impact along the whole route. We predict the arrival time of the next bus. We can predict that, so we know what the bus is, and we can predict how long it will take to reach a certain stop, so we can compute the headway at the stop, where the bus is waiting to be injected. And the idea is that the bus will be injected as soon as the headway exceeds a certain threshold we call L. And at the beginning, I will inject the bus at the middle of the interval. And you can think if it's a good idea to inject it at the middle of the interval, or should we inject it earlier than in the middle of the interval, or later of the. You can think of this for a couple of minutes. So the idea is here: this you have. If you have decided that the threshold is 20 minutes, and a headway comes of 15 minutes, you do nothing. You keep your bus waiting. 5 minutes waiting, 10 minutes waiting, 25 minutes, now we inject the bus, right? And now you have two headways of 12.5, and then 9, and so on. And the idea here is that you want to minimize the expected waiting time, which, by the way, you can show that is the expectancy of the square of the headways divided by twice the expected value of the headways. Now, if this is the expected value of the waiting time, this is a very important number for you. You really want your waiting time to be low. As I said before, people hate waiting, and it's probably the one they remember the most. So, and the inverse of the expected waiting, the expected headway, is the frequency. So if the frequency is it's going to be given because you know how many buses you have and you know how much time you will be optimizing. So at the end, what you really want is to minimize the expected value of the square of the headways. The fleet is constant, the expected value of h is also constant. We will focus on expected value of h squared. So optimal L for a single bus reserved for injection. Which L minimize expected value of h squared? Well, is we will assume that k will be the number of headway exceeding the threshold. So the idea here is you have a distribution of headways, you know the distribution, and you will be taking, let's say, 20 of these headways. What's the probability that one of them will exceed the threshold? 2 of them exceed the threshold. 3 of them. Depending on how many of them, it will tell you if you will be used or you will not use the injection. If none of them exceed the threshold, you will never use it. So the expected value of the waiting time depends on if you inject or if you don't inject. In this case, of course, if you never inject, well, you will have just the value of the expected value of h squared. But if the number of headways longer than the threshold is higher than with 1 or more, well, then you will be injecting and the waiting time will be smaller. And this is the result where we have here, depending on, you have a fleet of 10 vehicles, 20 vehicles, or 30 vehicles, so 3 cases. Here is how long you set your threshold, and this is the expected value of the square of the headways. And you can see that, of course, if your threshold is very, very high, you never use it. Depending if you have 10, 20, or 30 minutes, and therefore the waiting time is very high and identical. If you had set a threshold that is very, very, very low, well, you always use it, but you don't earn much because you just use it in the first headway that comes, and you have an impact like this. Of course, the more buses you have, the lower the this is 10 buses. The expected value is lower because you have fewer headways. And interestingly, if you have more buses than fewer buses, you adopt a higher threshold. You are willing to take a larger risk, right? At 20 minutes, in this case, I will inject a bus only if a headway comes from 20 minutes, because I have 30 opportunities for this. If I have only 10 opportunities, I will be injecting as soon as I get a headway larger than 16. And interestingly here, in this case, in the middle case where you have 20 buses, you will be reserving 1 bus for injection. So in some way you will be losing 5% of your fleet, which will not be operating. Your waiting time will be 5% larger just because you left 1 bus aside. However, this shows you that the gain we get by injection is 9%. So it seems to be like a good deal in this case. You lose 5% of your supply, but you win 9% of your waiting by reserving the bus. Also, you're not operating the bus, by the way, so you're saving in fuel and emissions. You can also compute this for more buses, not just 1 bus. Maybe what if I have 1, 2, 3, 4 buses waiting to be injected? And in this case, what you see is that as the injection fleet size grows, the optimal threshold decreases. Yeah? So if you have more buses, of course, you will be allowing to inject when the headway, the threshold is shorter. And also, it shows how the marginal impact of each additional bus is decreasing. So here you win a lot, you win a little bit less, a little bit less, a little bit less by having an extra bus. I think I am about to finish, so I will skip, and so to see if we can have some time for questions. Let me see if I can go to the last one, because the last argument I would like to make is this one. So at the end, a big thing here for me is that the future BRT, which was bus rapid transit, should be written with double R, and I think that's a main issue here. It should be bus rapid and reliable transit. The whole point of bus rapid transit is to provide metro-level service at the surface. And metro is not just fast. It's not just frequent. It's not just high capacity, it's also reliable. Much reliable than usually the buses are. So the question here is that if you want to do BRT, you should focus yourself not just in rapidness, but also reliability, and there are many strategies. I've mentioned two. Holding, well, three, bus boarding limits, but also mainly injection. You can also think of stop skipping, and you can think of many other ways in which you can increase reliability. So that's it.
Thank you very much for the very interesting presentation. I think we have time for a couple of questions.
I didn't hear a particular word. It's called snow. The weather delay. I've frozen very many days waiting for a bus.
There's two dimensions, two sides of this coin. One is the passenger. The second is the operation. On the side of the passenger, I would claim that what I've mentioned is all the most important, because the waiting conditions, when it's freezing, or when it's dark, or when it's unsecure, make the more important that people will wait a certain amount of time they are expecting to wait, and not more than that. So if a bus is supposed to come every 5 minutes and shows the unreliability I'm showing, and eventually it comes every 20 minutes, well, you may have some of your passengers not just pissed off, but also dead. I don't know. So this would be very, very, very relevant. The second side, so I would claim that this is the more relevant if you have difficult weather conditions for your passengers. Kind of the opposite of Disney World, when people are waiting seeing a movie and people don't care. If there's no movie but it's snow, it's much more difficult. On the side of the operators, I think the weather affects much more the variability of travel times. Now here I would claim there are two types of disturbances. Those that are really severe, in which the service can no longer be provided, and that's an issue that it's a different type, where you really want to have good communication ways, devices or systems with your passengers, so that they look for a different service because the bus will not come, or when it just makes the operating conditions more severe, and sometimes some of the buses may break down and may be taken out of the system. If you need to take some buses out of the system, our system shows, the holding system, where you, instead of having a schedule, you control according to buses actually are, it's much better, because it allows you to adapt your buses into an even headway service, even when you have to take 1, 2, or 3 buses out of the system along the route. And I think that also holding a bus in those conditions is not as terrible, because people are probably inside the bus when the temperature is not as bad and they feel comfortable and secure in comparison to being outside. So I think a holding strategy would work really well. Yes.
In your discussion, you mentioned that your optimization was based on estimates of passengers.
Yes.
What would be the improvement if we actually had reliable counts? Because the reason we don't get the super reliable counts is because of the additional cost, and the question now is, what would be the improvement that we could see if we had reliable counts of passengers either waiting or on the bus?
Yes, we have, to be honest and fair, here in the solution we assume that we know how many passengers are. So the results I've shown are assumed. But let's assume the opposite. Let's assume that instead of having the exact number, we only have estimates. And that's something we've done. And what we see is that if the excess waiting time with this service can be dropped by 60% or 70%, it's very severe. Instead of that, you end up losing like 10% of the benefit. So of course, it depends on how variable and how randomness you add to the passenger arrivals and how much information you have. But for normal arrival patterns, what you end up is that you lose like, instead of travel time variability and in terms of arrivals, you end up like 10% of the benefits.
One quick follow-up to the question earlier. One of the impacts of snow or ice or even rain is that the cycle time varies from day to day. And looking at your two strategies, it seems that your first one deals with that quite well, variable cycle times, whereas the second one not so well, because you're fixing the threshold, which really should be dynamic based on the cycle time.
That's a really good question. I agree. Not only that, I would claim, and that's something that the next steps that we're going to be doing, is that the threshold should even in a normal day, the threshold should also be dynamic. Like maybe if you're going to be there for 2 hours and you define that instead of saying, oh, I will inject a bus in a headway that is longer than 20 minutes, maybe during the first half an hour you will do it after 30 minutes. In the second half of an hour, if your bus is still there, you will drop a little bit the threshold into 25 and then to 20 and then to 15. And of course, in the case you're mentioning in terms of weather, you should also consider probably different types. The threshold should be set depending on directly on the cycle time. If there's reasons to think that your cycle time will be longer or shorter, then that should certainly affect how to define the threshold. Thank you.
Yeah, so you mentioned several times the metro system.
Yes.
And the metro system will have the same problem, not as much as the surface bus because you have a dedicated roadway. But it's high frequency, and right now, the reason why it doesn't end up bunching, because there are safety rules.
Yes.
You cannot have, yes, but those are not optimized.
Yeah.
Those are fixed. You cannot have two trains this close to each other for safety reasons. So, how much better would it be if it was optimized and not just a fixed threshold, don't be closer than half a mile or whatever?
So in this case, in the case of
The
metro,
metro is not perfect.
I know. And in the case of metro, as I said, also there's this issue where if the crowding conditions on a metro, because the metro has also one extra thing, which is they have lots of doors. So if the metro is operating under normal conditions where the train is not really packed and the platform is not really full, the dwell times at the stop shouldn't be that long. So the conditions are set so that it's uncommon that the headway will get large just because the bus is getting behind the train, behind the train in front. However, sometimes in the case of trains, there's two things that makes things worse. One is that they have some mechanical issues. I mean, it's not uncommon in our city that a door don't close, that a backpack gets trapped, and of course that extra 30 seconds, that extra 40 seconds make a huge difference in an operation that is one train every 90 or 90 seconds. This train that departed with 30 seconds lag will arrive to the next one, and there's going to be a 50% or a 30% more people waiting there. And of course, from then on, we will see the same problem here where the train will get delayed. And of course, the next one will have to be delayed for safety reasons. So what you see is that it's a drop in the frequency that you can achieve just because of this. The other issue is that when trains are really on complicated context, like from what you've seen from the Japanese videos you've seen of people pushing people inside the trains. This is something that happens in many cities. In my city, we don't have people pushing, but as some of you may have experienced, we really get sometimes 6-7 passengers per square meters in a train. That's not uncommon. And in these conditions, if people want to get out of the train in a platform that is full of people, that can take a really long time. So there's also the reasons for as you say for the need for this kind of service is also important in the case of metro, mostly because the headways can get too long, not necessarily because of headways being too narrow, because that is prevented by the control services.
One last question.
Yeah, Carlos. This is a supply side approach, right? And what I'm thinking is, like, if I knew for sure, okay, that after this really crowded bus, within 2 minutes, empty bus is going to come by, I would be perfectly willing to stand there for a couple more minutes and get on the empty bus. So what's the potential of a demand side? Okay, having the passengers be part of the solution by giving them information about how the system's performing.
Well, you mentioned that maybe passengers can give information like, oh, my bus is empty, but also, as I claim, the operator can also have that. We also have the information. If you know that a bus has always been trailing a very small headway, you know this bus is full. You don't need information. So I think that we should have, I imagine that here you have information on your apps on how much time for the next bus to come. However, it's very uncommon that they tell you how many people are inside the bus. I think that would be very interesting information, because if you know the next bus is coming in 2 minutes, and the next one in 5, and the 2, there's no way you get a seat, but in the 5, there's plenty of seats. That's valuable information for us to take the decision on which bus we will be boarding. And the interesting part of this is that you not only will be benefiting yourself, you will be benefiting all those people inside that bus that are crowded. All of them will be so happy that you're not boarding their bus. So there's an externality here that is very evident from providing this information, where you take a better, so I think yes, and I think this will be very easily to address by providing information to users, not only about how much time for the next bus, but also under which conditions this bus is operating.
Let me finish this session with one question, and I'd like to know if you have any remarks about emerging technologies. How does vehicle automation and vehicle connectivity help in regularizing Headway?
I think we have heard a lot about autonomous vehicles, and these autonomous vehicles are mostly planned as cars operating in any urban circumstance. And any urban circumstances are so varying that I think there's a lot of time yet to see them as commercial possibilities. However, I think they're following the wrong priority, the wrong path. I think we should install these autonomous vehicles first in buses operating in corridors. This tram here, I cannot imagine a simpler operating condition across all operating conditions in a city than those that are experienced by a bus or a tram in a corridor. You know exactly what kind of obstacles you'll see, what kind of circumstances will happen. You know exactly where your sensors should be implemented. So, and the good thing about this is that if we provide autonomous technology in buses, we can achieve much more than just safety, which is the main issue in the case of cars. With buses, we can achieve schedules. We can have regular headways. If we can control our buses to run autonomous, we can have a much close docking between the bus and the stop. So there's many issues. We can have a much smoother drive by the driver by having autonomous vehicles. So I think that, and especially because what we really want in cities is to operate our cities more efficiently. And the first thing we need to do is to make the public transport in general, more appealing. So I think that we should drift from having autonomous vehicles to autonomous buses. And the second thing is that we need to have some sort of technology which is not just about autonomous vehicles, but also connectivity between vehicles. Headway regularity is not achieved by just having an autonomous vehicle, but also some sort of control within the other vehicles. And I think that the autonomous cars should be a good, who may have a great impact on buses, because in many cities, vehicles enter into bus corridors, not respecting that this is just a bus-only lane, and by having some sort of control of the cars, we may be able to enforce more bike lanes, bus lanes. So I think if we can manage these new technologies towards a more sustainable city, this may become a good solution and a good solution for sustainability, for urban sustainability. If we don't, this could be a nightmare. So that's a big deal.
Thank you very much.